Welcome to Maths with EJD. This is the last video talking about the applications of integration, except if something comes up in future and I need to talk about application of integration in another area. So application of integration to volumes. We've talked about areas, application to areas. We've talked about application to kinematics. Talked about application to probability, and now application to volumes. I know volume is a three-dimensional thing, unlike area. So if you have a cube, you have length times length times length. That's length cube. So it's that. And if you have like a cuboid, you have length times breadth times height. And of course, you have other kinds of objects. And the unit is usually cubic units. For area, it's squared units. But here it's cubic units because you're talking three-dimensional. Okay. So that's a kind of foundation for that. So let's see how this applies. So for instance, one area with one aspect of volumes when you talk about application of integration is volumes of revolution. It's like spinning something over and then a volume is cut out. So when the graph of a function f of x is revolved completely around the x-axis between x of a and x of b, the volume generated in cubic units is given by this. So that is, when we're talking about area, right? We just did f of x. We did f of x dx between a particular interval. But here now, if we integrate the area between a and b, so if you integrate area dx between a and b, you get the volume. Okay? So, and usually you already know that area is pi r squared. And here we take our radius as the whatever function you're given. So that means you have pi f of x squared. So the function is like the radius, right? Because you're spinning it about its axis. So you have pi f of x squared dx. And then that can simplify to, pi is a constant, right? So you have pi into integral from a to b f of x squared dx. And that's it. So whenever you need to find the volume of revolution for a particular object, completely rotated around the x-axis, or I mean that also applies to the y-axis, except that now you now have y equals a and y equals b. Okay, so if you have that too, you can do that. So you need your function, and then just in the formula that the formula pi integral from a to b of f of x squared, whatever function you have, square that. So let's see how this happens. So I have some examples to show. Find the volume of the solid generated when f of x equals x squared is completely revolved around the x-axis between x equals 0 and x equals 2. Now look at this. F of x equals x squared is just a simple parabola passing through the origin. So you have this passing through the origin going up like that. But then we want to see it completely revolve around the x-axis between x equals 0. So you have x equals 0 and you have x equals 2 here. So it's like this whole thing. So when you spin it around its axis like that, so this kind of thing that came here, you're going to have that type here. And then you're still going to have this. And the whole thing forms into a kind of shape like this. All right. So it sweeps out a volume like you see here. And that is what exactly you can see on the right-hand side. So that's the idea we are trying to project here. Okay, like this hollow one gives us a kind of picture of what it ends up being. So whenever something like that happens and you need to calculate the volume of that revolution, then it's pretty easy. Just apply the formula. So this is the revolution of f of x equals x squared about the x-axis. So let's see how that works. Just apply the formula, right? The volume is computed as follows. Volume is pi integral from a to b of f of x squared dx. So here our f of x is x squared. So you square that again from 0 to 2. That has been specified for us. So you have x squared raised to power 2 is x raised to power 4. So that's integral from 0 to 2 of x4 dx. Of course, pi is outside. So if you integrate x raised to power 4, you have x raised to power 5 over 5, which is 1 over 5, x raised to power 5, now to be evaluated from 0 to 2. So to make your burden easy, take the 1 over 5 out. So you have pi, there was pi here, pi outside. Pi times 1 over 5 is pi over 5. And then you have x raised to power 5 from 0 to 2, to be evaluated from 0 to 2. So put 2 for x raised to power 5, you have 2 raised to power 5 minus, put 0 for x raised to power 5, you have 0 raised to power 5. And 2 raised to power 5 is 32, minus 0, you have 32. So you have pi over 5 times 32, and that ends up being 32 over 5 pi cubic units. Of course, you can simplify this further. You can say 32 times pi is roughly 3.142. Interestingly, yesterday was just Pi Day, 14th of March, or today. Yeah, was it yesterday? I think so. And 3.14. So Pi Day celebrated March, which is 3/14th, 3.14, right? So you have 32 times 3.14 divided by 5, and then you can get something in decimal. But I mean, sometimes it looks cuter to just leave it in terms of pi. So for f of x equals x squared, revolved around its axis completely, it forms a revolution whose volume is 32 pi over 5 cubic units. All right. So let's go to what else we might have. So I believe that should be another example. All right, we have another example. So find the volume of the solid generated when f of x equals square root of x is completely revolved around the x-axis between x equals 0 and x equals 4. Yeah, I'm sure that's, yeah, x equals 0 and x equals 4. Now, f of x is square root of x. That is x raised to power half. Now, if you plot x raised to power half, right, this is the kind of thing you're going to get. So you get this kind of shape, and between 0 and 4, this is 0, this is 4. So you have this whole thing like this. This is the region. So it is still an area for now. But if it is revolved, completely around the x-axis, so it comes out like this. It comes out smoothly like that. And you have this whole thing. You have this whole thing. And then it's now like a solid like this. All right. So it's like this kind of solid now. And then this is what the kind of thing you get. I actually got it for using GeoGebra. GeoGebra is one tool you can use. I've told you now about some of these tools. I've told you about Desmos. So if you see those beautiful plots I made, I used Desmos. I've also told you about Wolfram Alpha. You can do a whole lot with Wolfram Alpha. You can do quick fittings of data. Of course, that's maybe small. If you don't have too much data, you just want to do a quick fitting. So you can use Wolfram Alpha for that. And now I'm talking to you about GeoGebra. So these are very good tools for doing some fast math stuff and for visualizing some of these things. GeoGebra. That's what I used for this generation. You can see I had to impute all these things here to generate this. Okay, so that's f of x equals root x. All right. So how do you calculate the volume now? The formula is clear. So the volume is calculated as follows. Volume is pi integral from a to b of f of x squared dx. In this case, our f of x is simply square root of x, and square root of x is x raised to power half. Okay, so you have pi integral from 0 to 4 of square root of x raised to power 2 dx. Of course, square root of x raised to power 2 so the power cancels the roots, and then you have pi integral from 0 to 4 of x dx. So if you integrate x, you have x squared over 2, which is half x squared, and that's to be evaluated from 0 to 4. All right, so you take half out, so you have pi over 2, that's pi times half, pi over 2, and you have x squared from 0 to 4. Put the 4 for x squared, you have 4 squared. Put 0, you have 0 squared. So 4 squared minus 0 squared. 4 squared is 16, 0 squared is 0. 16 minus 0 is 16. So you have, so 2 here is 1, 2 here is 8. So at the end of the day, the volume generated by the revolution of f of x equals root x is 8 pi cubic units, 8 pi cubic units. And again, you can just get 8 times 3.142 and you get some results, if you like. So that's actually possible too. Okay, so now we are done with all the applications. So let's look at some exercise. I've shown you some of this before. I've shown you, so these first two are for they are for areas. These other two are for kinematics. And then I've shown you the ones for probability 2 the other time, where you get to talk about whether a function is a probability density function, how you can find the probability, within a range, and how you can find the expected value. And of course, this last two talk about volumes. So with that, you have everything sorted. Except that I also still need to show you, I've mentioned some resources that can be useful for you. So I have them right here again. I've told you about GeoGebra. So I use that for solid of revolution visualizer to visualize the solid revolution. Then of course, this is a very good calculus book. J has by MD Ware, early transcendentals, university calculus talking about early transcendentals, and then Desmos graphing calculator for all the graphs you've been seeing. Then of course, some other material right here. Thank you so much for listening. Be sure to subscribe to this channel and keep coming back. And how do you know when to come back? Um, Click the bell button so that when a new video drops, you get it straight and you get to know about it. Thank you so much. So this interestingly brings to the end basic calculus. So see you when I make another maybe a fast. So I also I get to do fast math solutions, right? I just quickly solve problems and then see you where next we can see. Maybe talking about fast math solutions or talking about another series uh of maths issue like trig or probability or anything close to that. Bye.